Okay, we are wrapping up chapter 4, I think. Why not? So last time we got into hybridization, and hybridization is the idea of bonding where we combine atomic orbitals. So we kind of combine atomic orbitals, which again are like S's, P's, and D's. And we combine them into these hybrid orbitals, which again, sort of the benefit of it is they have the same sort of shape. They also have the same energy, and it provides for sort of better overlap happening and better bonding. And hybridization is really tied to the electron pair geometry. And again, one of the easiest ways you could assign hybridization is to really just kind of count it off is probably the best and easiest way to do so. And when we do electron pair geometry or geometry in general, we do treat, as we talked about, everything as a one electron pair. So we treat, again, single bonds, double bonds, or triple bonds as one electron pair. So that is also how we go about counting electron pairs when we're doing hybridization. So if you have a single bond, double bond, or triple bond, it's all just going to count as one. And essentially, you know, if you count up 3 electron pairs, you always start at the bottom here and just go 1, 2, 3, and that would get you an sp2 hybridized sort of atom. If you had 4 electron pairs, 1, 2, 3, and 4, you would now have an sp3 and so forth. So really, it's kind of the easiest way to do it. Again, if you have multiple central atoms or wherever you may be doing, we do the same things what we do when we assign geometry. Again, we kind of hold our hand over one half and just look at each of the atoms individually. So when we have kind of the linear electron pair geometry, which is basically 2 electron pairs, that's going to be our sp hybridization. When we have trigonal planar, that's going to be really 3 electron pairs, which is our sp2 hybridization. When we have tetrahedral, that's 4 electron pairs. That's going to be our sp3 hybridized orbitals. We also talked about sort of sigma bonds and pi bonds. And remember, sigma bonds is head-to-head overlap of those orbitals. Badly drawn there, but they go straight at each other and they sort of overlap in this region here and come right at each other. And that is going to be our sigma bonds. Essentially, if you want to think about, like we talked about last time, kind of like the first line drawn is like a sigma bond. So, you know, if you have a single bond, it's pretty much going to be a sigma bond. When we have double bonds or triple bonds, they're made up of a couple different types of bonds. The first line there is the sigma bond, and then the rest of them are pi bonds. And pi bonds, again, are actually a result of the unhybridized p orbitals. So when we do something like sp or sp2 hybridization, we will have basically some some unhybridized p orbitals, and they overlap what is referred to as sideways overlap above and below the plane of the molecule. And this is basically what makes up a pi bond, is those unhybridized p orbitals. So we also saw as well that hybridization and hybrid orbitals can be bonding orbitals. They also can actually be non-bonding orbitals and have like the lone pairs, like we looked at with NH3 and water. Some of those hybrid orbitals are actually occupied with 2 electrons, which represents those lone pairs. Any questions on any of that stuff? All right, so let's just finish, I think, a little bit more on hybridization here. I think we did that guy, so we'll continue through that there. Now, when we talk about multiple bonds, again, we can get those pi bonds being formed, again, as a result of those sideways overlap, as we were talking about, again, above and sort of below the plane of the molecule. Now, what about expanded octets? Expanded octets can also hybridize, and that gets us into the d orbitals, right? Because that's where we have our expanded octets. That's why they can go above 8 because they have those d orbitals available to them. So kind of the same idea here. You could still count it off when you do that. And this is, again, as we saw earlier, our electron pair geometry. And again, we had our linear, which was SP, our trigonal planar, which is SP2, our tetrahedral, which is SP3. So adding to our list, if we go with our electron pair geometry, triangular bipyramidal, that is 5 electron pairs. So if we count that off, that's 1, 2, 3, 4, and 5. And that would give us a hybridization of sp3d. And we also can go to our 8 that we talked about with geometry, which is octahedral. And octahedral, or actually 6, not 8, but octahedral is the name. It has 6 electron pairs. And again, if we count it off, 1, 2, 3, 4, 5, and 6, that's an S, a P3, and 2 Ds gives us our sp3d2. So even with our expanded octets that we talked about, we could have hybrid orbitals, again, for those ones that have the ability to do so, and that will get you obviously into our Ds there. Questions on that there? All right, the last thing we're going to talk about here in terms of bonding is dipole moments and really molecular polarity. And when we talk about molecular polarity, we are talking about the entire molecule as a whole, all the bonds that are there, all the bonds taken into place, the geometry of everything. That is overall, is this molecule going to kind of share the electron density equally? Or are they going to share it unequally? And the result of unequal sharing overall is, actually, I'm going to draw it like this, maybe a little better. Go. So I guess if they're sharing unequally here overall, we'd have a lot more red on this side. Maybe not so much red on that side, right? So here in a situation where overall molecular polarity, we have overall equal sharing of electrons, that's going to result in a nonpolar molecule. When we have this unequal overall sharing of electron density in the entire molecule, that's going to result in, much like it does in a polar bond, a separation of charge, which means there's going to be a positive side to the molecule and also a negative side to that molecule, and that's going to be a polar molecule. Now, molecular polarity should not be confused with bond polarity. In most cases, they are different or can be different. Again, as we talked about earlier, and we'll talk about one more time here in a second, the only place really where bond polarity, and when we talk about bond polarity, we're talking about that difference in electronegativity values that we did, those calculations. And we're talking really with bond polarity, just really between these two atoms within a molecule. Are they going to be sharing electrons equally or unequally? Again, when we're talking about molecular polarity, we're taking the entire thing into account, all the bonds that are present and so forth. Now, if it is a polar molecule, it will have what is known as a dipole moment. And a dipole moment is actually represented with the same arrow that we used earlier with bond polarity. So we do use the same type of arrow as we did earlier. And any polar molecule will have a dipole moment. And the arrow basically works the same way as it did with bond dipoles. And what we had earlier was the arrow would point to the more negative side of the bond, and the back end here would be to the more positive side of the bond. In the case of a dipole moment, the arrow points to the more negative side of the molecule, and the back part here is to the more positive side of the molecule. So we definitely do use the same sort of arrow to represent bond polarity and molecular polarity and the dipole moment. Now, again, as I mentioned before, polar molecules are the only ones that will have a dipole moment. If it is a nonpolar molecule, it will not, because again, overall, it is equal sharing of electrons. And essentially, you have a neutral sort of molecule happening there. There's not a negative side or a positive side to that particular molecule. So let's talk about really the simplest molecular polarities you could do, and as we might touched upon in the previous chapter, that is the diatomic molecules. And the diatomic molecules are really the simplest ones that you can determine, is this molecule going to be polar or nonpolar? And that's because, frankly, they only have one bond in the entire molecule. So they're basically only made up of one bond. And because of that, this is the one place where bond dipole, bond polarity, and molecular polarity will definitely be the same. So we saw some examples. If we had H2, O2, when we look at the bond here between H2, that definitely is a difference in electronegativity of 0, which means it's a nonpolar bond. And once again, because that is the absolutely only bond that we see here in this molecule, that only bond is nonpolar, which definitely would make this, again, a nonpolar molecule. When we look at O2 here, again, the difference in electronegativity is going to be 0, as they both have the exact same electronegativity value. And once again, this bond right here is going to be nonpolar bond. And because that is the only bond that we have in that entire molecule, this will also make this a nonpolar molecule. So this is, again, sort of the one place where bond polarity, where you use the difference in electronegativity, and molecular polarity basically will be the same because they only have one bond. So whatever that bond is what type of molecule it would be. If you have some type of different heteronuclear diatomic molecule like HF, it's the same sort of approach. When we look at this bond, the difference in electronegativity is like 1.9, which tells us it's a polar bond, with the fluorine being more electronegative. So the arrow would point towards the fluorine in this case. And because that is the only bond here, that would mean that this would also be a polar molecule as well. And that means that this right here, the way it's pointing, would be the dipole moment in this case. And again, really what that's telling you is that the fluorine part of that molecule is more negative than the hydrogen part, which is more positive in this particular case. So definitely diatomic molecules, they're basically the same. Bond polarity and molecular polarity should come out the same because it only really contains one bond. Now, when we do have more than two atoms involved, and we have three or more atoms involved, we do have to kind of look at a couple different things to help us decide, is a molecule going to be polar or nonpolar? So when we have more than three atoms or more, we have to look really at two things. We have to look as, are there polar bonds? So clearly, in most cases, if there are no polar bonds, probably the molecule is not going to be a polar molecule. But if there are polar bonds, it means it could be a polar molecule. And the second thing that we would have to look at is the molecular geometry. So we do have to look at the molecular geometry here, or the shape of the molecule, definitely when we have three or more atoms sort of involved. So let's take a look at the classic example for this, which is our friend carbon dioxide. And if we draw carbon dioxide here in a little Lewis structure action, there it is, looks something like that. So the first thing that we want to think about is in carbon dioxide, does it have polar bonds? And the answer is yeah, it does. And I know that really without any numbers because when I look at the periodic table, I got that arrangement right there in the same row, carbon, nitrogen, oxygen, fluorine, and that's carbon and that's oxygen. And I see oxygen is further to the right, which tells me oxygen is going to be more electronegative and it's going to be basically a polar bond. So remember that if you're comparing somebody in the same row or the same group, you really don't need the numbers. You probably will have a polar bond if they're definitely not the same one in those rows or groups. You'll have some type of polar bond. So that means here, definitely, yeah, our carbon dioxide has polar bonds. It has a polar bond between the carbon and the oxygen. Again, the dipole arrows here for bond polarity would be pointing towards the oxygen as it is more electronegative. So the answer is yes, we have polar bonds here. Now, because it does have polar bonds, you may be tempted to say, I would think it should be a polar molecule because it does contain polar bonds. But that's why number two here is quite important, and that is we do also have to take a look at the geometry of this. And if we take a look at the geometry as a reminder, like we did last time, you want to go to the center atom, you want to find out the number of electron pairs. So that is one electron pair there, two electron pairs. Remember, everybody counts as one. And you want to know how many bonds you have, so that's going to be one bond, and that's going to be two bonds. And of course, you remember that something with two electron pairs and two bonds has a molecular geometry of linear. They're going to get 180 degrees away from each other. And because they are all bonding electrons, both the electron pair geometry name and the molecular geometry name are going to be linear, opposite ends of each other as far away as you get about a bond angle of 180 degrees. So what we have in this situation is basically a linear molecule like my pen. And on one side, we have oxygen pulling this way. And on this side, we have oxygen pulling the other way. And I'm actually pulling really hard on my pen in opposite directions. Is my pen going anywhere? No, it's not. Sound effect was for free today. All right. So what happens in this case, because of the actual geometry of this molecule, even though it does have polar bonds, they actually cancel each other out in this case. So they kind of cancel. And that means that this is actually going to be a nonpolar molecule. So this is a really good example of it is definitely possible to have a molecule that has polar bonds, but because of the geometry, it can actually be nonpolar. And so it's not a given that if you have polar bonds, you will have a polar molecule. Sometimes people think of polarity, kind of as a good example of it, like pulling on a rope, right? And like a tug of war situation. So, if this guy is pulling the rope this way and this one's pulling the rope this way and the little flags in the middle, mud pit in the middle as well. If they're pulling equal and opposites of each other, basically the rope's not going to go anywhere like my pen, right? So they kind of cancel each other out. Um, now, when we look at something like water, for example, draw a little water action there. And again, when we look at water, it does have polar bonds between the hydrogen and the oxygen, with the oxygen being more electronegative, heading in this direction. And in this case, we also need to look at, we do need to look at our geometry. So we go to our central atom here, and it has 4 electron pairs. Remember, we count everything dots, lines. It does not matter. Everybody gets counted as one. In terms of bonds, it has 2 bonds. So this is our bent, our V-shaped geometry, hence the drawing of it like so. Now, what we have in this situation is we again have polar bonds, and we got something like this, right? Kind of a geometry like this. And we got polar sort of bonds going this way and this way. You can almost think of it like the rope that's up on top, right? And if I had a rope on top and I just lifted, right, the whole thing would probably come up because they're all kind of combining up here as almost like the rope and one rope kind of pulling up, and it'll have movement. So what happens in this case is we do actually get a net dipole moment happening in this direction of the molecule. And that's because the oxygen here will now be more negative in water, and the hydrogen side of the water molecule is more positive because of this unequal uh, sharing of electrons. As you may know, these things, they call that vectors, I think, in physics, and vectors have direction, they have magnitude. I fell asleep at that point, but then I woke up long enough to remember in certain cases they add to each other, right? In certain cases they cancel each other out. So if you have some type of vectors heading in equal and opposite directions, they will cancel each other out, like my little rope example there. Also, if you have one heading basically right at each other, they will pretty much cancel each other out. You can think of it like a swinging door, right? If you have somebody on one side of the door and on the other side of the door, and they both push on the door's never going to open, right? It's just going to kind of stay there if they push equally. So it's not going to go one way or the other. They're going to basically cancel each other out. But in the case of water, what we have there, dare I give it the old college try here, kind of add your little vectors together, maybe with a net adding going in that direction. That's all I remember, maybe, and that's not very much, I don't think. And we get a net dipole moment going basically in that direction. So we do have to take into account these bond dipoles and polar molecules and really these vectors. And it also affects the size of it when you add, if they do add together, depending on the size of the individual bond dipoles, the difference in electronegativity as to how they will add together. And you can end up with a very small dipole moment arrow like that, but it's still kind of going in one direction versus maybe one is a little bit bigger. And you could do the whole calculation, which obviously we will not do in here. But nobody wants to do vectors, right? Otherwise, you'd be sitting in physics right about now, I imagine. So there must be a much easier way to do it, and I think there is. And there are some symmetrical geometries that we come across. And what we're talking about here, again, is the molecular geometries that we talked about. And that's the shape, basically. So for you guys, let's see, we have on that list, we have trigonal planar. We have tetrahedral. We have some of our expanded octets, triangular, bipyramidal. We have our octahedral. And basically what all these guys have in common is if you draw the Lewis structure and you look at it, they will have no dots, aka lone pairs, on the central atom. And if they have no dots or lone pairs on the central atom and all the outside atoms are the same, you are going to end up with, in pretty much most cases, a polar molecule. I'm sorry, a non-polar molecule. Let me say that correctly. I had a 50-50 chance there, but was thinking and I wrote the wrong thing. Non-polar molecule would be a much better thing. A non-polar molecule. And the reason you're going to have a non-polar molecule is they're going to end up basically being equal and opposite directions of each other. And again, if you think about the rope, they will all kind of pull at the same sort of equal and opposite directions, or they'll push at equal and opposite directions, and they're going to cancel each other out. So for example, here, if we take a little CF4, and again, I'm not going to draw all the electrons on the fluorine, but we definitely have, in this case, polar bonds between the carbon and the fluorine. So we definitely have polar bonds all the way around. But in this case, we have really no dots on the central atom. Everybody on the outside is going to be the same. This is going to be a nonpolar molecule because they're all going to go basically to the corners of a tetrahedral and pull that rope equally, and they're just going to cancel each other out in this particular case. Now, if I took the same molecule and maybe swapped out one of those fluorines for a hydrogen, I will now have some polar bonds going obviously towards the fluorines. And the carbon hydrogen bond's actually non-polar, right, in this case. So now if you want to kind of think about it, you got like three guys over here pulling the rope, and this guy on this side is not really pulling the rope in the opposite direction, right? He's just kind of hanging on. In fact, that is a difference in electronegativity of like 0.4. So it's not a perfectly equal sharing of electrons, but it's still considered nonpolar. In fact, he's actually, kind of helping just a little bit that way, as carbon's more electronegative than hydrogen, even though it's still considered a nonpolar bond. So you got kind of three people pulling one way, and the other guy's just kind of going with them a little bit or just hanging on. You can kind of imagine the whole thing's going to move. So it would now be a polar molecule in this case because of that. So if you have any of these symmetrical geometries and you have no dots on the central atom, everybody on the outside is the same element, it's a pretty safe bet, go nonpolar. If you have no dots on your Lewis structure and everybody on the outside is not the same atom or element, you should probably go polar is probably a safe bet, and that's a pretty quick way that you can do that. That then leaves us a lot, I think. That leaves us some unsymmetrical geometries. So some unsymmetrical geometries is pretty much everything that's left over for the most part. I'm going to try to remember all the ones you have. We have angular. We have trigonal pyramid. We have bent or V-shaped. We have some of those expanded octets. We have T-shaped, right? We have seesaw. And that would work. And then we have square pyramid, if I am not, or pyramidal. I think I hit them all. What did all these guys basically have in common? If you draw the Lewis structure for these guys, you will have dots or lone pairs on the central atom. And if all the outside atoms are the same element, it is most likely going to be a polar molecule. So that's a pretty straightforward one. That is why, for example, our water that we saw earlier, when I look at water, I see dots, I see the same element on the outside, I see it's a polar molecule without having to really think too much about it. Now, a lot of times you could do sort of molecular geometry is like dots or no dots is sort of a very quick way you could do it. There are two geometries that I did not put over here that actually do have dots. And those two geometries are are exceptions. I'm going to come back here to see some pictures of them. Maybe it should be around here. Go back to that there. Actually, let's do this here. Sure, keep it. Yeah. We'll go back to our chart like we had here. I'll probably see it better on this. My bad drawing. I'll just steal this chart. All right, so our two sort of geometries that do have dots that actually are going to be considered symmetrical geometries is our expanded octet linear. So not the 2 and 2 linear, but our expanded octet linear. And that is here. Again, what happens in this situation, as you kind of see here, we got the non-bonding electrons pretty symmetrical to each other in a triangle. And then we have our bonded guys opposites of each other in a straight line. So this as well, if you have the expanded octet linear, even though it does have dots and everything on the outside is the same element, it will actually be nonpolar. So that's one exception where, again, you could kind of have dots and so forth. The other exception is actually this guy right here, and that is square planar. And if you have a square planar geometry, which is our octahedral expanded octet, what happens is because it makes a square, those guys are going to basically cancel each other out. It's like everybody's going to be pulling opposite of each other. And those two non-bonding electrons will also sort of go opposite of each other and sort of cancel each other out in terms of that as well. So those are two sort of exceptions to the dots or no dots that you have to just be careful of. Expanded linear, expanded square planar. If you have either of those geometries and all the elements on the outside are the same, you're going to hit basically a non-polar molecule because of that. Now, as I mentioned before, I think I hit them all here. So this, again, anybody with dots will have basically be polar. So that leaves really the only one that you sort of have to think about is the 2 and 2 linear. So your 2 and 2 linear here. And that one's pretty straightforward. Again, if you have a linear sort of situation, and like we saw with CO2, everybody's going in opposite directions, it's going to cancel each other out. You could also have a situation, again, with the 2 and 2 linear, that they're heading in the same direction, and also the expanded linear as well. And they will cancel each other out. But it is possible that you could have in a linear situation everybody heading in the same direction. And in this case, it would actually be a polar molecule. If you take kind of the pulling on the rope example, if everybody's heading in the same direction, that means everybody's just pulling this way, right? And the whole thing's going to kind of move, and you can think of it as being polar in that particular case. Any questions on that there? So what that allows you to do is essentially, kind of geometry super quick. Let me go back to where we were, I think. Where were we there? Here, I think. Let's go here. All right, so if we take a look at, some of the stuff that we've drawn before, just kind of hit a few here. There. Do throw that one up there for fun. Why not? So we'll do this one here. All right, so if we just wanted to do sort of geometry really quickly here, we'll just do that one. All right, so if we wanted to do geometry, kind of like what we were doing there, what we would want to do, right, is take a look at it. And here, again, I see dots on the central atom. I see everything on the outside is the same. Polar and nonpolar, this one. This one's going to be, should be polar, right? So dots, everything the same. It's going to be polar. Here, I take a look at this one. I see no dots. Everything on the outside is the same. Going to be nonpolar, right? Take a look at this one. I see no dots. Everything on the outside is the same. Going to be nonpolar. I take a look at this one. I see dots. Everything on the outside is the same. Going to be polar in this case. Take a look at this one. What would this one be? Polar or nonpolar? This one has no dots, right? Is everything on the outside the same? It is not. So When we have no dots and everything on the outside is not the same, it goes from being nonpolar when they're all the same to being polar. And that's because these are all going to be nonpolar, but that's going to be a polar bond. So again, we have basically one person pulling on the string, and that's going to make the whole thing kind of move. This one, we actually need to look at the geometry here because this geometry is 1 electron pair, 2 electron pairs, and 2 bonds. That is linear in geometry. So we do have to take a look at it. And if we take a look at it here, the carbon-hydrogen bond is nonpolar. The bond between carbon and nitrogen is polar. Once again, they are in the same period. Nitrogen is further to the right. In this case, we basically have one person pulling only, and that's going to make this a polar molecule in this case. And lastly here, we got a diatomic molecule that is the same, guys, and that means that that bond's going to be nonpolar, and because that's the only bond there, this guy will be nonpolar. So that's as quick as you could do molecular polarity and probably be right in 99.9% of the time. Nothing's 100, I suppose, but you'll be right pretty much most of the time. Basically, dots or no dots is the quick, easy way of doing that. Any questions on that there? And if I had, let's say I had, that's way too many dots there. I'm gonna just kill some of those dots there. Dot crazy, I think. There we go. Let's say I had this one. This one would be, I didn't even count electrons. I'm hoping I did. Not too bad. There might be a charge on it. What is this one now? Polar or non-polar, this one? What is the geometry of this one? It is linear. It's the expanded linear we just talked about. Same thing on each side. That means this is going to actually be non-polar. So again, that's one of those exceptions. We got a nice little triangle in the middle for our non-bonding electrons that makes some symmetry. Any questions on any of that there? Got it. So as we were talking about, again, bond polarity and molecular polarity will definitely be the same in a diatomic. So here our HCl definitely has a polar bond, and it will result in a polar molecule. Our CO2, as we talked about, again, will essentially cancel each other out and really create a neutral molecule. There is no side where there's more electron density than the other, and it will result in a nonpolar molecule. Here, as you can see with our water, our net dipole moment heading in this direction, hence the more red spot of the coloring there means that there's a lot more electron density in that area. It's really hotter, which is why it's red there in terms of electrons. And there's our ammonia. Again, we do have our non-bonding electrons going in that direction. Once again, in this case, dots, everything's the same. Net dipole moment heading towards the nitrogen, which between nitrogen and hydrogen, nitrogen is obviously more electronegative, as you see by the points of those arrows. All right. Now, molecular polarity does affect a lot of things, as we'll talk about in later chapters. But again, a couple of things that it definitely affects is things like boiling points and melting points for substances. If things have really positive charges, they could do things like hydrogen bond or dipole-dipole interaction, which are referred to as intermolecular forces, and that's the way they interact with other molecules, including molecules that are similar to themselves. They also play a tremendous role in solubility and how things mix, as we'll talk about in later chapters. There is a saying that is like dissolves like, so things that are very similar in terms of how they can interact with themselves, which is really based on is the molecule going to be polar or non-polar. They then can react with similar type of molecules the same way, and that makes them mix really well. If you get somebody that's, for example, as we'll talk about in a later chapter, somebody is non-polar and somebody is polar, they're going to have an extremely hard time interacting with each other really well because, frankly, one has a charge and it wants to interact through like positive negative interaction. The other one's neutral, and it can't do that, and that makes a really bad situation, hence the kind of oil and water mixture there. Oil is pretty much nonpolar, which means it's kind of neutral in a sense, and water is polar, which means obviously it has a positive side and negative side. Water likes to use something known as hydrogen bonding. Oil can only use what's known as dispersion forces, which are super weak interactions. And over a long period of time, they just can't interact well with each other. That's why oil will float on water, if you ever see an oil leak or anything like that. Also, a really benefit of that is like soap, for example. Soap actually has a polar side and a non-polar side, and that works really well for soap because dirt is typically non-polar. So when you roll in with some soap, what happens is I'll just draw them as lines right now. The non-polar side of soap, which is actually this part right here, all the carbons and hydrogens, it just surrounds the dirt basically. And what it does is it allows the polar side, I'll just put the little charge on this side. It has the polar side basically out in front around it. And that's really good because usually when you use soap, the next thing you use is water, yeah. And water is polar, as we just saw, where again, the oxygen is more negative, the hydrogen is more positive. So the water is going to be able to interact with the polar side of soap that has now trapped your dirt on the non-polar side, and it goes out with the water, basically, right? And you're clean and happy at that point. Always good to know how soap works, I suppose, right? All right, so if we take a look at these last two here, are these going to be polar or non-polar molecules? Take a moment and decide. There are some electronegativity values if you need. Okay, so let's take a look. So we'll do both ways, I guess. So we first want to think, is there polar bonds or non-polar bonds? So obviously the difference in electronegativity between nitrogen and chlorine is 0, which means this bond here is actually non-polar. The bond between nitrogen and oxygen, the difference in electronegativity there is 0.5, which means it is polar, and it is going to head towards the oxygen in this particular case. We also then need to look at the geometry here, and that is a central atom with 3 electron pairs, 1, 2, and 3, and also 2 bonds. That's going to give us our angular geometry, which means basically if we draw this a little bit more accurate in a sense of how it is sort of shaped, like something like this. So essentially, if you just think about it, we got something on a triangle. I'm just going to pull on one side of it. You can just imagine the other side is going to topple over, right, and start to move. And this guy would be polar, right, overall in this terms of molecule. Now, if we look at the second one here, we have sulfur and oxygen. Difference in electronegativity for all those is 3.5 minus 2.5, which is 1. That definitely is a polar bond. So we have a polar bond heading that way. We've got a polar bond heading that way. We've got a polar bond heading that way. And once again, we're going to look at the geometry here. Central atom, we have 3 electron pairs. Remember, everybody counts as 1. So 1, 2, 3. And we have 3 bonds in this case, which again is also 1, 2, and 3. That means that this is trigonal planar geometry. That's basically a triangle. So if I draw this in my best triangle-ish type way here, we basically got this situation happening, right? And basically we got everybody pulling on the corners of a triangle, which means they're all going to cancel each other out. And this is going to be a non-polar molecule. First off, any questions on that way of doing it? Now, clearly, did you really need to do that way of doing it? Probably not. And as you'll see, right, you'll be all right. So I would prefer perhaps just to do it this way that we just talked about, which is, let's see. My important thing to look at is I see dots. I see everything on the outside is actually, in this case, not the same. But even if you went with just the dots in this, you would be okay because it's going to be polar in this case. At that point, what you have to do is just think about the bond. Here we have no dots. Everything on the outside is actually the same. And that means it's going to be nonpolar, which is, again, a much quicker way of doing that. And I still hit the right answer there on both of them, right? So, again, a much quicker way to kind of do molecular polarity. Any questions on that there? All right. I think that wraps up this chapter, I think. Yeah, I think so. All right, that wraps up this chapter. We're going to roll back to now chapter 3. The last section there that wasn't covered the first time we rolled through chapter 3, which was the bonding part of it. We're going to talk about nomenclature. We're going to talk about how to name everything. And you'll be naming professionals, hopefully, by the time we are done. We are already naming professionals. That'll be good, too. All right, so nomenclature basically is, as you know, hopefully, is how we name things. And it really is sort of broken up into two types of sort of compounds that we talk about. And those are ionic compounds, as we know from our speech on bonding. That's usually a metal and a non-metal. And that usually is a cation being involved and an anion being involved. And again, no sharing of electrons. We talked about it again. It's that electrostatic attraction, right? That holds that together in that case. So if it's an ionic compound, we name it differently than if it's more sometimes referred to as a molecular compound or covalent. And that usually involves a couple of nonmetals, just like it does in bonding, and involves obviously sharing of electrons. And again, if we have sort of two nonmetals or a covalently bonded compound, we do definitely name it different than we do ionic compounds. So let's get into this here. That is the periodic table. And again, a reminder that there's a lot of colors on that periodic table. There are certain elements that will make fixed charges, right? So when we look at the periodic table, just a reminder that if it is in group number 1 here, it's going to be a +1. Group number 2 is going to make a +2 charge when it does make a charge. Really in group 3 here, it's aluminum is most of the time that we deal with. We kind of skip group 4 and then heading here 5, 6, and 7. That typically is backwards here, -3, -2, and -1. Again, we're talking about the nonmetals above the staircase here, as they will make anions that will make those charges. As we go that way. Now, in terms of the transition metals here, as you may remember and know, they can make a variable positive charge. In addition to the transition metals, just to the right of the transition metals, underneath the staircase, in sort of this region here, we will have some guys that can make a variable charge as well. So even though they're not transition metals, technically speaking, they are kind of the staircase, which makes them metals. They also do have a variable charge, things like tin, antimony, lead, bismuth, those guys can also make a variable charge. Now, within the transition metal region, there is a 3-pack of elements that can and do have actually a fixed charge. And that is right here. So zinc and cadmium, if you hang a left there at cadmium, over there to silver. Those 3 guys, although they are transition metals, they have a fixed charge, and the fixed charge is for, let's write over here, zinc and cadmium is going to be a +2, and if hang a left there to silver, +1. So those are kind of 3 exceptions in the transition metal region that even though they are transition metals, they also have basically a fixed charge. So obviously that's really important in terms of nomenclature and writing formulas. Make sure you understand those charges. So let's continue on here. Now, when we talk about ions themselves, and we talk about cations and anions, there's a couple important things to remember. Ions obviously have charges, and a cation is positively charged. And as we talked about, that is a result of it losing electrons. Anions are negatively charged as a result of them gaining electrons. And when we have a cation, we want to write the formula for a cation, we do need to include the charge. So if you were asked to write the hydrogen ions, cation there is H plus, sodium would be Na plus, calcium would be 2 plus, aluminum there would be 3 plus. So first off, if you are asked to write the formula for an ion, it does need to include the charges. So if you're just writing the ions formula by itself, it does need to be the charge. How do we name a cation? To name a cation is pretty simple. We just simply use the element's name. So this would be the hydrogen ion. This would be the sodium ion. This would be the calcium ion. And that would be the aluminum ion. Now, anions, which are negatively charged, obviously, if you're going to write the formula for an anion, you do need to include the charge as well. So hydrogen is one of the only ones that could go both ways. So it can be positive in certain cases, and it can be negative in other cases. You did something like Cl minus, Br minus, N3 minus, O2 minus. Now, the way that we name negative ions is a little bit different. Negative ions, we take kind of the first part of the name, some part of it, and we drop the last part and we put IDE at the end of it. So instead of hydrogen, this would be the hydride ion, IDE. Instead of chlorine, this would be the chloride, IDE ion. Instead of bromine, this would be the bromide ion. Instead of nitrogen, this would be the nitride ion. And lastly, instead of oxygen, this would be the oxide ion. So negatively charged ones will have IDE at the end of it. Positively guys, just going to use the whole name of the element. The only way we usually will come across the negative version of hydrogen is if it comes after a metal. So if you had something like, for example, LiH, that is lithium with a +1 charge and hydrogen with a -1 charge. So if hydrogen comes after a metal in an ionic compound, it typically is going to be the negative version. I would say 9 times out of 10, maybe even more than that, it's usually the positive version is the one you come across, but it can definitely be negative here. Now, by the way, when we do take a positive ion and a negative ion and we put it together, we always want to make sure the formula has no overall charge. So if we had a sodium ion and an oxide ion and we wanted to put them together for the formula for an ionic compound, we need to make sure that both of those charges, when they're added together, will equal 0. In this case, we would need not 1 sodium, but we actually would need 2 sodiums in this case. And that would get us 2 sodiums. Number always goes to the guy to the left. And 1 oxygen. Nothing written there means 1. Also goes to the guy to the left. So we always want to balance out the charge in an ionic compound. The formula for an ionic compound, much like we see here, should never ever have a charge, but it is actually made up of things that do have charges. So that's an important thing to remember when we see sodium oxide, which is Na2O. It does not have a charge. It's actually made up, as you can see there, of 3 ions. The reason it's made up of those 3 ions and the reason we need to balance it to 0 is what we talked about in the bonding chapter at the very beginning when we did ionic bonding. The purpose of ionic bonding, right, and all kinds of bonding is for everybody to get to the noble gas configuration for electrons. So if you remember the example we did, which was this example, calcium and fluoride, we said calcium cannot get rid of both of its electrons to 1 fluoride. It needs 2, right? And that's going to allow calcium to reach noble gas configuration. And that's why when we put it together, we have 1 calcium and 2 fluorides there, yeah? And that gives us our proper formula. So as we talked about in bonding, the reason why when we put together a positive ion and a negative ion, we want to do so in the simplest way to get to 0 in terms of the charge is it basically allows everybody to get to that noble gas configuration, right? That's why, by the way, we needed not 1, but 2 sodiums, right? Because if we only use 1 sodium with the oxygen, and we just use 1 sodium, and it went over like so. Sodium's good, right? Because the sodium got to noble gas configuration, but our friend oxygen only got to 7, right? Which is kind of like 8, but not making it there, right? So that's why, again, in this case, need that extra 1. And that, again, is really why it ends up like this. Yeah, it's really that bonding thing that we talked about in that previous chapter as to why we need to balance out to 0. And when you do that in the simplest way possible, it just gets everybody to that noble gas configuration in that stable sort of sense. Any questions on that there? So here's a table, and again, you can see just whole names here for anybody that's a positive ion. And once again, IDE treatment. And depending on the element, we do take a little bit more than the back end of some of those names, but this should end in IDE. So let's talk about type 1 compounds. So type 1 compounds are going to contain a metal and a nonmetal. And frankly, as we talked about when we talked about bonding, as soon as you see a metal and a nonmetal coming together, you should automatically think this is going to be an ionic compound, right? Now, the deal with naming is the thing that is most important in terms of naming, especially if a metal is there, is always the metal. The metal is always the one that basically tells you what you need to do in terms of naming. So the metal here is what we're referring to as being a type 1 metal. And a type 1 metal is a metal that has a fixed positive charge. And that, as we just talked about, is basically on the periodic table, group 1, group 2, group 3, which is aluminum, zinc, cadmium, or silver. So if you come across any ionic compound that has a metal that comes from group 1, group 2, group 3, zinc, cadmium, or silver, you should automatically know it's a type 1. The good news on that is you can basically just roll right into the naming part of it, and that is the whole name of the metal, and the nonmetal will get the IDE treatment here. So the whole name of the metal and the non-metal gets the IDE treatment. So for example, obviously here, NaCl, the first thing we can look at, Na is Cl is a non-metal, so that tells me it's ionic. As soon as I see the sodium here, that is my metal, which is a type 1 metal because it is group number 1, has a fixed positive charge, will never be anything other than that. I can roll right to the name, which is sodium, and again, IDE for my second one there, chloride. Now I have something like CaBr2, right? I take a look at this. I see Ca, which is a metal. I see Br, which is a non-metal. I know that this is ionic. I want to always look at the metal. Most important thing, calcium is group number 2, which means it has a fixed positive charge and going to be a type 1 metal. And that means I'm ready to roll right into my name, which in this case, I'll go over here. Whole name of the metal. Non-metal is bromide here. Yeah. So that is calcium bromide. That is not, by the way, calcium dibromide, unless you would like an X. Yes. We do not use a prefix. It doesn't matter if you have 144 of those. Don't use a prefix here. Yeah. So it's just bromide for the second one. The reason for the 2 is what we were just talking about a second ago. The reason we have 2 is this guy does not have a charge, but it's basically made up of a calcium ion, which is the cation, and not one but two of these bromides, which are anions. By the way, if you were asked to write the formula for the anion, that is the correct formula. This is an X. Yeah, so there is no Br2 minus. Yeah, so you want to be really careful. Those are common mistakes people make. Simple rule is this: if you have a metal, you should never touch a prefix in that naming unless you want it to be wrong. So you should never use a prefix with a metal if it's there. So that's a good way to remember, should you use a prefix or not. If you have a metal, don't use a prefix. It's wrong in this case, yeah. Any questions on that there? All right, so why don't you take a moment here and name these? Why don't you also write the formulas for, I don't know, let's do sodium phosphide. Let's do magnesium. We'll go chloride. Actually, we'll swap this one out for something different since we already did that one. Let's do SR. I'll do that one instead. Let's do here aluminum oxide. All right, so names on the left there, formulas on the right. See what you come up with here. All right, let's take a look. We'll start the first one here. You might want to identify what it is. K is potassium, which is a metal, and Cl is a non-metal, so that automatically should tick the box for ionic. Whenever a metal is involved, that is the most important thing, and that is potassium, which is group 1, which means it has a fixed positive charge, so that should put a little check mark next to type 1, and that means that's all you really need. You roll with the whole name here of our metal, potassium, and IDE there for our chlorine, which becomes chloride. This again is made up of a cation that is K plus and an anion that is -1 chlorine there. Question on that one. Next one, we got zinc, which is a metal, sulfur, which is a non-metal, again, checking the ionic box. Zinc is actually a transition metal, but it is one of those three that we talked about that has a fixed positive charge, which means it is going to be considered a type 1 compound. And that means we could roll to the name a little zinc and some sulfide here, IDE. This is made up of a cation that is zinc with a +2 charge and a sulfide with a -2 charge, which is why we only need one of each of those when we put them together to get to 0. The quick swap out here on the next one, Sr is strontium, that's a metal. Nitrogen is a non-metal, so that is ionic. Strontium is group number 2, I hope, and that means it's going to have a fixed positive 2 charge, so we can roll right into strontium and nitride here, IDE, made up of a strontium with a +2 charge, actually 3 of them as the subscript supplies, and a nitride that has a -3 charge and 2 of them. -3 is -6, and 3 + 2s is +6, gives you 0 when it's all said and done, and that is how we get there. This is barium, which is a metal, and hydrogen, remember, is actually a non-metal, right? So this is really ionic. This is a case where we have barium that is +2, and group number 2, which means is a fixed positive charge, is a type 1. So we could go barium. This is a case, though, where hydrogen comes after a metal. This is the negative version of hydrogen. So this is barium hydride. That is barium with a +2 charge, and not one, but 2 of those guys hanging out in this particular case. Any questions on any of those names there? Rolling the other way here, we want to basically write the formula. So sodium is a metal, phosphide is phosphorus, which is a non-metal, so I know it's ionic. So I just really want the basic ions to make this up. So sodium is group 1, which means it has a +1 charge. Phosphorus is group 5, which means it has a -3 charge. So again, in this case, we need to get to a 0 charge. So if it helps you, you could just draw it out or draw them out. I need 3 of those sodiums, right? Which means my formula should be 1, 2, 3 sodiums, as that goes that way, and 1 phosphorus there, right? Now, sometimes people are taught to just do that move right there, just bring things up, bring things down. And that works, like 93% of the time. So if you're good with 93% of the time, if you just want blindly sort of move the things up and down, you'll get it right about 93 or so percent of the time. But it will not work 100% of the time. So I would recommend maybe just think about it, properly. And again, if you just kind of switch them, you'll get it right sometimes, but not all the time. All right, magnesium is a metal. Chloride is a non-metal. And here magnesium is group 2. And chloride is group 7, which means it's -1. Once again, when we put this together, we do need equals 0. If you're not sure, you can just multiply the two numbers. 2 times 1 is 2, which means we need one more of this guy's over here to get to 2. That is 1 magnesium and 1 and 2 Cls. There it is, right there. And lastly, we have aluminum, which is a metal, and oxide, which is oxygen, which is a non-metal. Again, it's going to be ionic. Aluminum is group 3, which means it has a +3 charge. Oxygen there is group 6, which has a -2 charge. Once again, if you just multiply the numbers together, that is 6. So we basically need to get everybody to 6. So to get my aluminum to 6, I need not 1, but 2 of them. To get my oxygen to 6, I need 3 of them. So 1, 2, and 1, 2, 3. There's the proper formula. Any questions on that there? So type 1, not too bad. Fixed positive charge. We could roll right into the naming on it. Any questions? All right, we will lay it up there. I think